The silence is almost religious. In a hangar the size of 12 football fields, 4 million individual components await their transformation into a single flying machine. Screws smaller than grains of rice unite with 40-meter fuselage sections, creating the Airbus A380, the largest passenger aircraft ever built by humanity. Each A380 emerging from this industrial cathedral incorporates 550 tons of aluminum, 130 kilometers of electrical wiring, and 320 kilometers of hydraulic tubing. There are 2,300 windows installed one by one, 22 landing wheels capable of supporting 560 tons, and 4 engines that generate force equivalent to 3,500 Formula One cars. But here's the reality that defies comprehension. These 4 million parts arrive from 1,500 suppliers spread across 30 different countries. A single wing contains 32,000 components manufactured in 8 distinct nations. The cockpit incorporates 130,000 electrical wires that, if connected in a straight line, would cross all of France. How is it possible that components manufactured on different continents fit together with precision of tenths of millimeters? How do engineers coordinate the simultaneous arrival of millions of parts, each with tolerances that don't allow error exceeding 0.1 millimeter? And how does this logistical symphony create a machine capable of transporting 850 people at 11,000 meters altitude? The answer is hidden in the depths of one of the most complex manufacturing operations ever attempted by humanity, where Swiss precision meets gigantic industrial scale. Prepare to discover how billions of components transform into the greatest triumph of modern aeronautical engineering. The A380 story began with an impossible dream in the 1980s. Jean Pierson, from Airbus, observed congested airports and imagined an aircraft so large it could transport twice as many passengers as any existing aircraft. His vision faced universal skepticism. Many considered it physically impossible to make something so massive fly. The project officially began in 1988 as A3XX, when Airbus decided to challenge Boeing's monopoly in the large aircraft market. Jürgen Thomas led the first studies, discovering it would be necessary to completely reinvent aeronautical manufacturing. No existing factory could accommodate an aircraft of such dimensions. The launch decision in 2000 marked the largest investment in civil aviation history, 25 billion euros. 4 European countries, France, Germany, United Kingdom, and Spain, united resources and expertise, creating unprecedented international collaboration. Each nation assumed responsibility for specific aircraft sections. The first flight in 2005 was a historic moment. Claude Lelay and Fernando Alonso piloted prototype MSN-R001 in a flight of 3 hours and 23 minutes that proved giants really can fly. Crowds gathered in Toulouse to witness what many called the miracle of modern engineering. Certification challenges almost defeated the project. Aviation authorities demanded tests that had never been performed, like evacuating 850 people in 90 seconds using only half the emergency exits. Evacuation simulations with real volunteers proved the impossible was possible. Entry into service in 2007 with Singapore Airlines marked a new era in commercial aviation. The inaugural flight SQ380 from Singapore to Sydney transported 455 passengers in unprecedented luxury, proving the A380 was not only viable, but revolutionary. The A380's epic journey begins at 4 final assembly locations spread across Europe. Toulouse, France, receives fuselage sections. Hamburg, Germany, produces cabins and equipment. Chester, United Kingdom, manufactures wings. And Getafe, Spain, builds stabilizers. Each location operates like a symphony of industrial precision. Section manufacturing uses gigantic autoclaves, pressurized ovens the size of train cars that cook carbon fiber panels at 180 degrees Celsius under 7 atmospheres of pressure. Each fuselage section emerges as a monolithic piece, eliminating thousands of rivets and reducing weight by 20%. Wing assembly happens in specially built facilities in Chester. Each A380 wing measures 36 meters wingspan and contains 32,000 individual components. precision robots install 150,000 rivets with tolerance of plus or minus 0.05 millimeters, while laser measurement systems continuously verify geometry. Section transport is an epic logistical operation. Beluga XL, specially developed cargo aircraft, transport fuselage sections across Europe. Wings travel by special barges through rivers and canals, on journeys that can last weeks and require coordination with authorities from 6 countries. Final assembly in Toulouse is where magic happens. A380 assembly line operates in sequential stations where each aircraft remains 8 weeks. 750-ton cranes position sections with millimetric precision, while 1,200 specialized technicians work simultaneously on each aircraft. Systems testing subjects each A380 to 2,500 individual verifications before first flight. Hydraulic simulators test flight controls, pressurized chambers verify cabin sealing, and fuel systems are tested with 320,000 liters of real kerosene. At the heart of A380 production is CATIA V6, three-dimensional design software that allows 15,000 engineers in 30 countries to collaborate simultaneously on the same project. This digital twin of the A380 contains every screw, every wire, every component, modeled with atomic precision, enabling detection of interferences before physical manufacturing. Advanced assembly robotics uses 7-axis robotic arms with 15-meter reach, capable of positioning 2-ton components with 0.1 millimeter precision. Computer vision systems guide robots through artificial intelligence algorithms that learn and adapt to component variations. Additive manufacturing revolutionized complex component production. Titanium 3-dimensional printers create parts impossible to manufacture by traditional methods like air ducts with complex internal geometries. Each printed part is 40% lighter than conventional equivalents, saving tons in final weight. Laser measurement systems continuously scan each section during assembly, creating 3-dimensional point clouds with billions of coordinates. Analysis algorithms compare real measurements with digital models, detecting microscopic deviations that could affect aerodynamic performance. Augmented reality guides technicians through complex procedures. Smart glasses overlay digital instructions over real components, showing exactly where to install each part. Tracking systems verify each step was completed correctly before allowing progression. Predictive artificial intelligence analyzes production data to optimize workflow. Machine learning algorithms predict bottlenecks before they occur, automatically adjusting delivery schedules and resource allocation to keep production flowing perfectly. The obsession with perfection in A380 assembly transcends any known industrial standard. Each aircraft must pass 15,000 individual tests before being considered flight-ready, with tolerances requiring precision superior to Swiss watchmaking applied to a building-sized structure. Structural fatigue tests subject components to 150,000 pressurization cycles, equivalent to 30 years of commercial flights, in just 6 months. Testing machines apply loads up to 1,000 tons, simulating extreme turbulence, heavy landings, and emergency maneuvers. Ultrasonic inspection examines every weld, every joint, every structural connection. High-frequency transducers detect defects smaller than 1 millimeter in 40-meter-long structures. Automated systems scan 100% of the structure, creating 3-dimensional maps of structural integrity. Electrical systems testing verifies functioning of 130,000 individual wires through complete flight simulators. Each circuit is tested under extreme conditions, from -55 degrees Celsius to +85 degrees Celsius, simulating Arctic flight conditions to tropical desert. Redundant systems ensure any component failure doesn't compromise safety. Engine certification requires each Rolls-Royce Trent 900 or Engine Alliance GP 7200 to pass 150 hours of continuous operation tests before installation. Test chambers simulate flight conditions, including ice ingestion, torrential rain, and debris, ensuring safe operation in any environment. Test flights subject each A380 to 100 hours of flight under progressively more demanding conditions. Test pilots execute maneuvers that will never be performed in commercial operation, verifying behavior in extreme situations and validating all safety systems. The A380 represents a silent revolution in aviation environmental efficiency. Fuel consumption per passenger is 20% lower than previous generation aircraft, while carbon dioxide emissions are reduced by 15% per kilometer flown. Each complete flight saves the equivalent of removing 200 cars from roads for 1 year. Advanced composite materials constitute 25% of the structure, replacing traditional aluminum with carbon fiber that is 50% lighter and infinitely more corrosion-resistant. Material recycling allows 95% of components to be reused at aircraft end of life. New generation engines use ultra-high bypass technology, reducing noise by 50% compared to conventional aircraft. 3-meter diameter propellers operate with 45% thermodynamic efficiency, superior to many power plants. Combustion systems produce 80% fewer nitrogen oxides. Sustainable manufacturing uses renewable energy in 60% of production operations. Solar panels and wind turbines power factories, while heat recovery systems capture residual energy from composite material curing processes. Optimized logistics reduces component transport through optimization algorithms that calculate most efficient routes. Load consolidation and multimodal transport. Air, sea, land reduce supply chain carbon footprint by 30%. Compensation programs plant 1 million trees for each A380 produced, creating forests that absorb carbon dioxide equivalent to 20 years of aircraft operation. Renewable energy projects financed by Airbus generate clean energy sufficient to power entire cities. The biggest challenge in A380 history was coordinating 1,500 suppliers in 30 different countries, each producing components that had to fit perfectly in final assembly. Digital management systems created a virtual control tower that monitors production in real time, detecting delays before they affect the assembly line. Wiring problems almost defeated the project in 2006. Software incompatibilities between German and French factories created 130,000 wires that didn't connect correctly. Emergency teams worked 18 months completely redesigning the electrical system, developing new digital communication standards. Infrastructure limitations required construction of completely new facilities. No existing hangar could accommodate the A380, forcing construction of 150-meter-wide buildings without internal columns. Airport runways needed reinforcement to support 560 tons maximum weight. Giant section transport created unique logistical challenges. 36-meter wings didn't fit in any existing cargo aircraft, forcing development of Beluga XL specifically for the project. Special routes through European rivers required modification of bridges and locks. Evacuation tests seemed impossible with 850 passengers. Simulations with real volunteers used exact cabin replicas, testing evacuation under smoke, darkness, and simulated panic conditions. Emergency exit innovations and 12-meter slides made safe evacuation possible. Simultaneous certification across multiple authorities, FAA, EASA, CAC, required standards harmonization that had never been attempted. Unique test protocols were developed, allowing a single test battery to satisfy regulations from all countries. The A380 transcended its function as transportation, becoming a flying city that redefines air travel concepts. Private first-class suites offer double beds, showers, and complete offices at 11,000 meters altitude. Social lounges allow passengers to interact during 16-hour flights, creating experiences impossible on conventional aircraft. Ultra-long routes directly connect cities that previously required multiple connections. Singapore, New York, 19,000 kilometers, becomes a single 18-hour journey, eliminating stopovers and reducing total travel time. 850 passenger capacity democratizes international travel, reducing per-seat costs. Hub airports use A380s as traffic concentrators, allowing passengers from smaller cities to access global destinations through a single connection. Dubai, Singapore, and London became global superconnectors, processing millions of passengers through A380 fleets. Air cargo uses A380 freighter versions to transport 150 tons of goods on intercontinental flights. Giant industrial components, medical equipment, and perishable products travel in pressurized and climate-controlled compartments. Executive Aviation adapted A380s as private flying palaces for heads of state and billionaires. Personalized configurations include conference rooms, multiple bedrooms, gourmet kitchens, and even garages for luxury cars transported inside the aircraft. Humanitarian missions use A380s for mass evacuations during natural disasters. Emergency configurations allow transporting 1,000 people in temporary seats, evacuating entire populations from disaster zones in single operations. The A380's future is being rewritten by technologies that will completely transform commercial aviation. Hybrid propulsion will combine traditional jet engines with electric motors powered by hydrogen fuel cells, reducing emissions by 75% and noise by 90%. Autonomous artificial intelligence will enable completely automated flights, where AI systems will make all flight decisions, optimizing routes in real time based on weather conditions, air traffic, and fuel efficiency. Human pilots will become supervisors of intelligent systems. Self-healing materials will incorporate nanotechnology that detects and repairs microdamage automatically. Molecular sensors will continuously monitor structural integrity, alerting about maintenance needs before problems develop. Adaptable cabins will use movable walls and reconfigurable seats to optimize space based on demand. Virtual reality will create artificial windows showing any desired view, while circadian lighting systems will automatically adjust to minimize jet lag. Sustainable Supersonic will combine A380 efficiency with Mach 2 speeds, reducing flight time by half while maintaining competitive fuel consumption. Variable geometry engines will optimize performance for both takeoff and supersonic cruise. Space manufacturing will use orbital stations to build components in zero gravity, creating structures impossible on Earth. Metal alloys formed in space vacuum will be 10 times stronger than terrestrial materials. Hypersonic transport will evolve A380s to Mach 5 speeds, connecting any point on the planet in less than 4 hours. Scramjet engines will operate at the edge of space, transforming commercial aviation into suborbital flights. The epic journey of how billions of components transform into the A380 reveals one of the greatest achievements of human collaborative engineering. From microscopic screws being installed to gigantic sections being united by colossal cranes, we witness a symphony of precision that challenges the limits of the possible. 4 million components from 1,500 suppliers in 30 countries represent more than numbers. They're testimony to a species that learned to collaborate on planetary scale to create machines that defy gravity. Each A380 incorporates collective knowledge of 100,000 engineers, decades of aeronautical innovation, and technologies operating at physics limits. The revolutionary technology behind this epic assembly, from CATIA software coordinating global design to 7-axis robots, from additive manufacturing to predictive artificial intelligence, demonstrates how impossible ambitions drive innovation. Processes that coordinate millions of parts with atomic precision, systems that detect microscopic defects, machines that operate with impossible tolerances. Absolute quality emerges from this orchestrated complexity. Aircraft that transport 850 people at 11,000 meters aren't engineering accidents, but products of meticulous science applied at industrial scale. Each test, each verification, each control parameter ensures flying machines are safer than any other means of transport. The civilizational impact transcends aviation. The A380 democratized intercontinental travel, connected distant cultures, and proved international cooperation can create wonders no single nation could build alone. The global village exists because we learned to make giants fly. This is the story of how humanity transformed impossible dreams into flying reality, coordinating billions of components in a precision dance that culminates in commercial aviation's greatest triumph. A380 assembly is not just an industrial process, it's the materialization of limitless human ambition, where global cooperation creates machines that touch clouds, testimony that when humanity unites, it can literally move mountains and make the impossible fly. Now that you've discovered the secrets behind the epic assembly of the world's largest aircraft, one question remains: how will you see airplanes with new eyes? The next time you board a flight or see an aircraft in the sky, remember you're witnessing the result of one of the most complex manufacturing operations ever attempted by humanity. Each aircraft represents perfect coordination of millions of components manufactured in dozens of countries, united by precision that defies comprehension. Share this revelation with friends and family. Show them that commercial aviation isn't just transportation, but one of the greatest achievements of international cooperation. Let them discover that each flight is sustained by technology more advanced than spacecraft, coordination more complex than military operations. Tell us your experience. What was the most impressive moment of this journey? Did you imagine a single aircraft incorporated components from 1,500 different suppliers? What other collaborative engineering marvels would you like to see unveiled with this level of detail? Challenge your perception about cooperation and precision. How many other products around you require equally sophisticated coordination? Smartphones, automobiles, buildings. Each one may hide a fascinating global collaboration story. Value the engineering behind safe aviation. Aeronautical engineers, specialized technicians, and test pilots dedicated entire careers so you can fly with absolute safety. Each commercial flight is a tribute to human genius applied to the millennial dream of flight. The aviation revolution continues, creating increasingly efficient, quiet, and sustainable aircraft. You are now part of this discovery. Spread the knowledge and help others see the extraordinary engineering that allows us to touch clouds with absolute safety. Special thanks to Airbus and its engineering teams that opened their doors, metaphorically, to reveal the secrets behind this extraordinary aviation achievement. To the teams of aeronautical engineers, materials specialists, and technicians who dedicate their lives to making the dream of flight a safe and accessible reality. Deep gratitude to commercial aviation pioneers, visionaries who imagined aircraft capable of transporting hundreds of people across oceans, and innovators who transformed dreams into flying machines. Your contributions made it possible to connect the world through the skies. Special recognition to advanced manufacturing systems, developers, precision engineers, and global logistics specialists who elevated aeronautical assembly to the level of scientific art. Each innovation represents years of research dedicated to the pursuit of flying perfection. Tribute to workers who operate in high-precision environments, handle safety-critical components, and ensure each aircraft meets the most rigorous standards in world aviation. Although systems are automated, brilliant human minds designed each process and continue innovating to achieve impossible safety. And primarily, gratitude to you for dedicating your time to understanding the complexity and beauty behind processes that normally remain invisible. Your curiosity fuels our passion for unveiling the secrets of the factory-made world. Research and narrative, factory-made team technical consulting, aeronautical engineering and advanced manufacturing specialists, scientific review, aeronautical testing and safety certification laboratories. Continue exploring with us the mysteries of modern aeronautical engineering. The world is full of extraordinary processes that create the machines that allow us to fly, waiting to be discovered. The next time you fly, remember, you're being transported by one of the greatest achievements of human collaborative engineering.